thanks to the organisers for the invitation. And I'm really looking forward to the other two talks in this really exciting meeting today. So as I say, this is a talk on machine learning and data assimilation with some input from various people around ECMWF, although I should say it does not in any way kind of cover all of the machine learning stuff that's going on at ECMWF. There's just too much to cover, but it's really much more focused on the machine learning with data assimilation side. So just to jump straight in, the biggest news of the last few years in weather forecasting is really this incredible performance of new data-driven weather forecasting models. Now, obviously, Stefan is going to have an entire talk on this, so I only just want to touch on it. But to say that you can already go to the ECMWF charts website and you can pull down charts showing the weather forecast based on various different data-driven models, including GraphCast, ECMWF's own one, AIFS. And from this forecast score chart here as a function of forecast day, you can see that the basically best medium range physical-based weather forecasting model, the IFS, is showing lower scores than all of these data-driven models. And I think I put a star on it. Machine learning weather forecasts are now outperforming in some circumstances, and I won't go into the details. It's difficult to verify forecasts exactly, and it depends what you're aiming for, but in this basic figure, you can see that the machine learning forecasts are predicting a day ahead of the physical forecast. And this is really exciting and a great challenge for the physical methods that we've been used to using so far. Now, jumping back to standard data assimilation, just to introduce really the visual language I'm going to use for the next few slides, because obviously we're all data assimilators here mostly, but if I have time on the x-axis and the fit to reality on the y-axis, and this is our typical data assimilation cycle, not caring too much about the timings of there's a forecast from day 1 to day 2 and all the observations are on one day, but the timings don't really matter. And what we do is, based on one analysis, we run a physics-based forecast model forwards into day 2. We compute the equivalence of the observations that were seen during that assimilation window, and we use data assimilation to improve the fit of the model to reality. So the analysis is a much better fit to reality than the original forecast. And so the process continues. And in the early days of data-driven forecasting, the idea was to fit, in general, to train your machine learning model against physics-based forecast models. Of course, that has the problem that you can't learn to forecast any better than the physics-based reference model that you're using. So one of the key steps forward in the recent years for the data-driven forecasting is to train against the analysis. So the machine learning model is trained between the analyses, typically from the ERA 5 reanalyses. And that's a really important step forward, I think, because it means that the quality of the machine learning model forecast can be better than the physics model on which the data assimilation is based. And that's clear, increasingly clear to see. So in terms of this y-axis of this graphical language on these figures, that the machine learning based forecasts coming from initialized from the same analysis as a physics-based forecast might well be better. And we will attribute that to the presence of the observational information in those analyses. And what I want to take from that for the data assimilation and the physics-based modeling thing is really a great big challenge that clearly current physics-based forecast models could be a lot better. That if a machine learning model can do an extra day's forecast skill, then there's something that the physics model is doing that is not doing. It's got errors that should be corrected. There are parameterizations that need to be better. And many people for a long time have been looking at parameter estimation and really trying to use observations to inform better physical models. But progress has not been very fast in this area. And really, this is an existential challenge to the whole idea of parameter estimation and improving forecast models in the traditional way. But I think it should be a really motivating challenge for us if we're in the physics side of things to try and do better and really start using the enormous amount of information that's in those observations to make better models. So how should we be using observations to make our models better? We've seen the pure data-driven methods, and we'll hear a lot more about that later. Parameter estimation I've skipped over, but really the focus of this talk would be what I call hybrid empirical physical modeling, which I'll explain as we go along, or machine learning to provide an online bias correction, which will be later in the talk. And so those are the two specific applications I'll focus in on. But I think they're pretty much the main ways that we will continue to be able to use a combination of physics-based techniques and empirical techniques as in machine learning. And this talk, although it would be great to go into other important ways we can use machine learning in data assimilation, such as generating massive ensembles, automatic differentiation, or fully replacing current data assimilation algorithms, data assimilation in the latent space of the machine learning models, and so on. All of that's really interesting, but it's not going to be covered in this talk either. And of course, Ronan will be talking later with some really interesting stuff on that area. So really just focusing on this talk on, as introduced, just the basic links between machine learning and data assimilation, and then how do we merge them together. So going back to that cartoon of data assimilation, and I want to take the components here and just replug them slightly so that we have a forward model, and the model is taking input called X from the analysis at day 1. It's running, again, the time periods don't really matter, but in this case, it's running an entire day's forecast, a 24-hour forecasting period based on a physics-based forecast model, and a lot, as well as generating the forecast trajectory and the states along that forecast trajectory, it's also generating observation equivalents, because without those observation equivalents, you can't do data assimilation. And so we can put that all together into a model Y is H of X and W, and I haven't introduced W yet. So W represents all of the equations and parameters in that physical model, and that's thinking in the way that all of the physical equations could be learnt themselves. If we had all the different possible differential equation representations in there, we could learn parameters to select which particular representation actually represents the physics and so on. So the W here for the physics-based model represents all of the equations in that model as well as the parameters. And this is the forward model basically used in 40-var data assimilation and 40 ensemble methods. So for weather forecasting, we're training, for data-driven weather forecasting, and we're training a machine learning model between states X and Y, which in this case are the analysis at day 1 and day 2 in this example. And here W has the meaning of the weights of the neural network, but it's the same basic equation that we can write down. And if we use this exactly the same, well, X is exactly the same as in the physics-based version. Y here is an analysis, but in reality, as data assimilators, we know that the analysis is a best estimate of the actual state of the atmosphere, but where that best estimate comes from, as well as the forecast, is from the observations, and that our true source of all the information on the atmospheric state is either physics or observations. And so we can again really make that equivalence between training a machine learning model. In the future, it's not going to be training on analyses, it should be training directly on observations. So again, we have essentially the three same identical components in that forward model, only this forward model is being trained. So we can put that all together into a little diagram. Well, this is a Bayesian network, which I'll explain over the next couple of slides, but just ignore that for the moment. And just think about the three different basic variables involved in machine learning training or data assimilation. We have the state of the atmosphere, we have the weights or parameters of the model, W, and we have the observations. And traditional physical data assimilation, strong constraint, holds the weights and parameters of that model absolutely constant and uses the observations Y to estimate a better knowledge of the state X, whereas traditional, you might call it strong constraint machine learning, assumes that you know nothing about the model, but the state X and the observations are perfectly known, and it uses exactly the same variational techniques to infer the parameters of the neural network. And the Bayesian side of this, it's really just a useful visual language here to represent the complicated equations of machine learning, of data assimilation, and the ways that's put together and the ways it's solved in a kind of good physically based way. So just to show you this diagram, X, Y, and W represent essentially in the Bayesian sense a probability distribution, a joint probability distribution, and that can be factorized using basic rules of probability. You can rewrite those equations into a couple of steps. Really don't bother with the details of this unless you're interested, and many people know this already, of course. And from that diagram, assuming x, w, and y are Bayesian probabilistic variables, you can get back to the Bayes rule for how you would update your knowledge of x and w given y, the observations, given the forward model, which in probabilistic terms here is the probability of y given x and w, and given the prior probability of x and w, the weights and the state. And using Gaussian error assumptions, we can take those basic Bayesian probabilistic equations and rewrite them as a variational cost function for data assimilation, as we use in 4D-var and similar. And here the aim is to minimize the cost function to find the best estimate of x and w. And assuming here just a single scalar variables for simplicity, representing no correlations between the states, the observations and the states and the knowledge of the model. We have these uncertainties sigma x, sigma w, which represent the prior knowledge of the state, the prior knowledge of the model, and sigma y, the error in the observations. And we have the well-known observation loss term and prior terms, background terms for the state and for the knowledge of the model. And from the machine learning side, we can basically take that same equation y equals h of x and w. We can also work out how we're going to train that from that basic Bayesian description. And in the machine learning world, we call it a loss function. And the typical loss function might again be a squared error norm between the observations and the observations simulated by the machine learning network. We don't generally do knowledge of the state term, but we do weights regularization. So that really is the basic equivalence between machine learning and data assimilation. It all comes from that Bayesian basis that we're just either traditionally trying to learn the state with physics-based data assimilation, or trying to learn the weights of the neural network model if we're doing machine learning. But of course, there's a great continuum of different applications between that, and increasingly each side is growing more physical in terms of machine learning, or more empirical in the side of data assimilation, tending towards parameter estimation. So we go back to that Bayesian network. This is just a little element of the whole data assimilation problem, and we know how to solve it because we have Bayes' theorem. I showed you very quickly how to solve this Bayesian network. And if we plug that into the time evolution of the state, so the state x1, x2, x3, x4 represent, for example, different days or different time steps of a forecast model. The model has parameters that are, in this example, time constant, and observations are taken that within the time window of each state. So given the observations, we already know how to update the parameters and the state to get better knowledge of the forecast model and the state. We can then forecast forward to get the next state. We can apply Bayes' theorem again to update the parameters and the state from the observations, and so on, forecast forward. And you can see that the more observations you get, the very much more information you get on those model parameters W if they are time constant. So you get an enormous amount of information on the parameters from this kind of process. Now, the other thing is you can break that model down. You can look at each time step as a series of, for example, different physical processes. So going from x1 to x2 might be the time step of one physical forecast model with a dynamic scheme, a cloud physics scheme for the atmosphere, radiation, and so on. As I mentioned earlier, in a data assimilation context, you're always having to generate observation equivalents, which are these Ys, here representing all sky and clear sky observations. And this is where we get to the idea of hybrid physical empirical modeling. If we've described our model as having weights, and these models could either be held fixed, let's say our dynamical core, we know the physics equations are really well, we assume that those are perfect, so we can hold the dynamical core fixed, and that's a physical model. But if we don't trust our physical modeling of clouds, for example, the W clouds, the parameters of the cloud physics model, we could throw away our physical model and plug in an empirical model and try and train it in the same data assimilation framework. And so we could have a mix of empirical and physical models all trained together with the physics constraining where the information from the observations goes in terms of training the weights of different models. This is not just a theoretical concept, it's happening right now, and that's the first example of two that I want to present. So this is the work I actually showed earlier at one of the ISDA sessions, but I want to revisit it here in that bigger, broader machine learning and data assimilation context and show some of the updated results from that. So this is a very complex slide, so I don't want to introduce it all straight up. I'm going to take it piece by piece and come and build back up to what you see here. So please don't get worried about this big network so far. But what we see in front of us is a slightly more complicated Bayesian network representation of what I'm doing in this hybrid empirical physical network work. So first of all, just to state the problem. So the problem is for using observations over sea ice, and the properties of the sea ice are very complex, not well known. And when we're making a satellite observation, we're measuring the radiation that's propagated through both the sea ice and the snow on top of it and the atmosphere and got to the satellite. That's in microwave frequencies. And an observation operator, again, this would be the forward model for using those observations, would represent that process. And the problem is that we don't have these observation operators or sea ice properties easily to hand. Now, if we did have the observation operator and we didn't know the physical state of the sea ice, we would be able to do data assimilation inversion and retrieve the sea ice properties if we had a really good observation operator. If we had the sea ice properties, we knew them very well, we would be able to do, nowadays, we would think, well, let's go ahead and do machine learning to find our new observation operator. We'll train it between the knowledge of the sea ice properties and our knowledge of the observations. And that would be great. Only the problem is, and this goes for most of these situations where you would want a machine learning observation operator, you don't actually know the properties, the inputs to your forward model, and you don't know the forward model particularly well either. And then you need to find some combination of data assimilation and machine learning to solve the problem. So what we have there is, well, I'm going to explain how that's solved now, through showing you building up that Bayesian network from slightly more atomistic perspective. So first of all, imagine if we did know the radiative transfer of the atmosphere, and we did know the surface emissivity of the ocean surface, both for sea ice and for water, but we didn't know the sea ice concentration. Then this little network would describe that surface problem and the atmospheric problem. Just to introduce the way this is written here, so the solid black outlines are for variables that we think are perfectly known, or we at least set constant, then they're not really perfectly known. The solid thin outlines are for variables that are dependent variables, and the dashed lines are for parameters that are trainable. And so this is basically showing a description of how you would retrieve sea ice concentration, that would be the trainable variable, from AMS2, these are these microwave observations, given good knowledge of the atmosphere and the sea ice emissivity. And it's the contrast between those two surfaces that enables you to detect the sea ice concentration. But of course, the sea ice emissivity isn't well known. And also, sorry, I've just got my animations wrong here. So instead of trying to train at the observation location, we're going to try and build up maps. So we've gone from a retrieval problem to now a data assimilation problem where we're trying to build up maps of the sea ice. So that's what these circles here are indicating, essentially an interpolation operator going from a map to the sea ice at the observation location. And then the point that the sea ice emissivity is not well known, we need an empirical model in this work to tell us what that sea ice surface emissivity is in order to be able to assimilate those observations and infer the sea ice concentration. So in this work, I started with a very simple neural network to give me the sea ice emissivity, and that's going to be a function of both the weights W and Z, which represents known physical inputs to that network. So for example, we do have a reasonably good estimate of the surface temperature from the atmospheric analysis, but we also need all these parameters, which I called X ice here, which represent all of the really interesting and detailed physical properties of the sea ice and the snow on top of it that actually strongly affect the radiative transfer and change the brightness temperature that you measure by hundreds of Kelvin in some cases. And those are the things that we don't know. So we don't know them, and we don't have physical constraints for them in this simple network. So all we can do is find empirical properties. So this is really the key to this particular empirical physical network, is both recognizing that the model is going to be empirical, but because we don't have any big source of really good training data on those microstructural properties of the sea ice and snow that we really need to know, we're just going to do our best to estimate an empirical version of those variables. So here, X ice is those statistical properties of the sea ice that affect the observations. And just like for the sea ice concentration, it's going to be learnt on a map, and there's going to be an observation operator to map to the properties of the sea ice at the observation locations which are needed for each observation. So we build up this whole network where the three main trainable parameters based on a cost function against the AMSA2 observations over an entire year's worth of data. We're going to estimate daily maps of the sea ice fraction, daily maps of empirical parameters representing the sea ice state, and training the neural network model for the sea ice emissivity all at the same time. This only works if you put in a lot of regularization, which I don't have time to talk about, but it's obviously really important to getting good results here. Practically, this lives in Python and TensorFlow. You can see all the code of this particular network on GitHub now, and this is just an example of the sea ice surface emissivity neural network layer. It's more complicated than it could be, simply because it both implements the neural network layer. This is basically a custom layer in Keras and TensorFlow. But when you call that layer as part of the training, it also updates a loss function. So as I was saying, there's quite a lot of regularization to make this work. And in this case, you define custom loss functions to constrain the output surface emissivity to make it relatively physical. And there's a lot of that going on in the network. So just to really show a few very quick slides on the results from that model was trained. So the surface emissivity model was trained offline and then plugged into the ECMWF forecasting system. And this schematic tries to illustrate what's going on there. And it's used to assimilate AMSA2 and GMI microwave imager observations over sea ice surfaces to add that to the data we already assimilate over plain ocean surfaces. The empirical state and the sea ice concentration are estimated here at observation locations rather than on a map, but that's one of the main differences between the offline training and the online use of this network. And the second big difference is that the neural network weights, for simplicity, are trained offline in the offline TensorFlow network and then used online in the Fortran code of the weather forecasting system, but they're held fixed. So then we, as I say, we estimate the input parameters for this empirical model at each observation location. We run the standard radiative transfer modeling process to update the atmospheric state and so on. Is that coming up to 5 minutes? Yeah, great. So just to give some very quick results on that. So this is just showing where the observations are being added over the polar regions. This is the first time we're able to assimilate these satellite channels in these areas. The forecast quality is better, so these blue hatching basically just show you that at, say, 3-day forecast, the southern hemisphere temperature forecast is improved at 60 degrees south. So this assimilating data over sea ice really brings new information to the forecast, and it also brings really nice pictures of sea ice. And this is just an example of the large icebergs being estimated in this system without going into detail. So what that system is doing is it's going to be operational in the next version of the IFS in autumn 2024. And that's really great. It'll be one of the first machine learning components being used in the IFS. And there's plenty of future development to be had in that system, including possibly training it online in the future and developing it physically. So I also wanted to show the bias correction thing quickly. We still have about 5 minutes. So if we had that time evolution of the cycled data assimilation, but we wanted to add error correction to it, then we'd need a Bayesian, an elementary Bayesian network that looked a little bit like this, with now weights representing a physical model and weights representing an error correction to that physical model. So X1A is the physically predicted state, and then it's error corrected by the error correction model, which might be a neural network. And we can train that error correction neural network based on the observations, and we can train it simultaneously with our analysis of the better state, but we can hold the physical model constant, and that's the idea in this work, is to keep the physical model constant, not to replace it, not to update it, but to learn an error correction to have a combined physical and empirical correction model that gives a better forecast state. And so you can update it from observations, you can forecast the next state, and so on. You can carry on with the cycle. So a lot of work is going on already, both with learning neural networks to correct errors offline for the full ECMWF system, and then really exciting work to start doing simultaneous online training of the neural network that corrects the errors alongside training the state. And that's this OOPS 4DVAR work, where the model is not the full operational system yet, but it's a quasi-geostrophic model instead. And that uses key technologies like the Fortran neural network library. And to very quickly present the results from that work, without error correction, the model forecasts a relatively high error. And if you do an offline neural network bias correction, the results get better. If you do online correction, better again. So that's really promising. To give an illustration of the impact that could have on the full operational scale forecast model, this is our scorecard, applying an offline trained neural network bias correction for the full ECMWF system. And blue is really good. That means reduced errors. So this is really promising. And the point there is that can bias correction using online or offline neural network bias correction training start to pull the results of the physical model back towards the quality of the empirical models? That's really exciting. So just to go into final thoughts, we've really got big decisions to make at ECMWF and many other weather forecasting centres as how to go forward. Are we going to stick with the physics on its own? No, because clearly empirical models are better. Are we going to do a kind of granular hybrid empirical physical network like I'm showing in this model time step on the left? Or are we really looking at something more like a foundation model for the Earth system, a great big neural network system that propagates states from one time to the next, that's X1 to X2, and also simulates observations so that it can train directly from observations? So that's the question. What resolution will it have? Will it be able to support all the observations that we currently assimilate for data assimilation? Will supporting those high resolutions and all of those observation outputs make that foundational model quite big? We don't know. It probably won't make it as big as a physical model, but it's still a question. And then the question that I was really trying to raise, especially in that sea ice segment that I was showing, is what happens if we need intermediate states and parameters of the model? In my case, it was the sea ice concentration, which we could extract physically, or the sea ice properties, which had no physical constraint, no observational constraint, so we could only get an empirical version of that. And that's the problem with the machine learning side of things, is your parameters don't have a physical meaning. So if you wanted, for example, the cloud parameters intermediate to predicting the state, you wouldn't be able to get them from the weights of the model. You could make them part of the state, in which case you'd have to learn their meaning from an existing physical analysis, or you could take special purpose observations, for example, of those cloud parameters like the cloud shapes or something, but you need a special aircraft to make those measurements in situ, and it's quite hard to turn that into training data. So the hybrid granular approach for me is the way forward. You're probably clear from the presentation, and it's happening already. I've showed you examples of how it works, but the real question is how to implement it practically in a real system, and that's really where the fun starts, especially when we start wanting to continuously retrain these things for many very good reasons. Do we have the technical tools ready for Fortran neural networks? Are our existing minimization strategies for data assimilation good enough? If we really are trying to do things properly and in a Bayesian way, we're going to have to specify the uncertainties of all these different parameters in the model in a way that means we can put the information from the observations where it actually belongs physically. That's a huge task. Just the same problem as I mentioned for the the machine learning thing is that for all of these less well-known variables, we really need to start incorporating research site data and aircraft data and very special purpose measurements to get access to these important physical variables that we don't observe in other ways. And finally, parameter estimation, we've wanted to do it for a long time, but why has it been so hard? That there are a lot of difficulties in doing this, so it's a really hard problem. So why do we want to do it the hard way if we've got a nice new easy way to do it with data-driven forecasting? And for me, it's just the Bayesian point that physical knowledge is prior knowledge that in a Bayesian sense should reduce the posterior uncertainty, and it should help us to give physical meaning to unobserved variables. And that really is the Bayesian perspective. Ultimately, with physics, we should get a better result than without. So thanks for listening, and I hope I've left time for questions.
Thank you, Alan. That was a really interesting talk. Yeah, we have a lot of questions. We have about 7. Maybe you can answer some of them live, and for the rest of them, you can just go to the Joepad and answer them. I will start as sequentially as they were posed. The first one is by Abhishek Lod. He says, you said that machine learning based data simulation models are trained from ERA 5 reanalysis. What was the time period of the training? And why are they not trained from observation or other backgrounds available? What is the significance of this type of the type of training and time period in the machine learning?
I would defer part of that question to the next talk, that you'll see a lot more about the training against reanalysis and the training time periods and so on, I'm sure. But to answer the question, why not train against observations? It's so much more difficult. The data assimilation puts the observational information onto a regular grid, and it puts it into physical variables that we're interested in. Satellite observations are sensitive to many different things simultaneously, all filtered through the radiative transfer of the surface and the atmosphere. And it's very hard to unpick that and turn it into physical variables. And so that really would be the next frontier for the data-driven approach, is to start learning from those observations, but to recognize that, for example, in the data assimilation section or area at ECMWF, at least 2/3 of people are working on observations rather than data assimilation methods, because the observational problem is so big that it just takes a lot of people and a lot of work. So if you can train from the analyses, that's a much easier starting point.
The second question is, at what resolution does the machine learning based model work? Is it the same as the physics based model, or is it a lower or different resolution in general?
And again, a question that's going to be answered in the next talk, but generally so far they're lower resolution, both in terms of time steps and in terms of space. And so that's really one of the points I was trying to make in I think is this slide here is just like, if we can get the data-driven models up to the point where they're simulating the physical state of the atmosphere every 10 minutes, like the ECMWF model, at 9-kilometer resolution and covering all of the different parameters of the atmosphere, including, I don't know, hydrometeor water contents and stuff like that. That's a lot more output variables than they're currently generating. For example, they're skipping over the whole of the 12-hour forecast period and going just from let's say day 1 to 12 hours ahead, and then from 12 hours ahead to 24 hours ahead. So whether that's really going to be a problem, or whether machine learning has the capability to handle that in its stride, is going to be really interesting to see in the future.
And let's answer a last question online. This one is from Tobias Berg from DWD. If you learn the equations in the dynamics and also learn physics parametrization, could this represent some kind of potential double counting?
I don't see it, and I think I'm on the right slide here, is that I want to show an instance of where there is double counting, but it's completely covered in the Bayesian methods or variational methods that we use. So, for example, here the cloud parameters are important both to the cloud physics, because they impact the development of the clouds, They're important to the radiation because clouds change the heating rates and so on. So the same parameters crop up in the radiation model inside the forecast model. And finally, those same cloud parameters affect the radiation that is observed by satellites. And so all those parameters are shared by different components of the system. But as long as you correctly specify your Bayesian network or your variational data assimilation system to propagate the sensitivities of those different components of the system back to the same set of parameters, there shouldn't be any double counting of those particular parameters. And here I'm hoping that, say, the dynamics parameters and the clouds parameters are entirely separate and have separate meanings. Otherwise, in this Bayesian sense, there would be they would either be the same variable or they'd be linked in some way through a dependency.
Very well. In that case, in the interest of time, we're going to leave the rest of the questions in the Jopad, and Alan can answer them directly. And we are going to move to our next speaker.